Can you guys see the screen and hear me?
I can hear you.
And you can see the screen, right?
Yeah, I can.
We review what we discussed in the last class. Unfortunately, for some reason, the lecture didn't get recorded. So last time we wrapped up chapter 4 with the discussion of what's known as a continuity equation, which, as I mentioned, is a bookkeeping equation which lets you keep track of what happens to the carrier concentration at a certain location as a function of time. So if you look at a one-dimensional problem with whole transport along the x-axis, for example, I'm looking at a semiconductor sectional area of A, then on a per unit area basis, suppose we have a current density JP flowing in at location X into this volume which is shown shaded of thickness between X and X plus delta X. So at X, we have a current density amps per centimeter square flowing in, and at X plus delta X, a current density JP evaluated at X plus delta X flowing out. Clearly, if there's more current flowing in than flowing out, the carrier concentration of holes within that volume as a function of time, delta P, delta T, will increase with time, right? If there's more holes flowing than flowing out. On the other hand, if there's more holes flowing out than flowing in, del P, del T should go down with time, okay? So then what you can do is you can calculate the difference between the currents as JP at X minus JP at X plus delta X, and divide that by the charge of the hole, which is Q, and then divide that by the volume, which is, if I'm looking at a current density problem, the cross-sectional area is 1 times delta X. So that then in the limit gives you minus del JP del X, okay? If this was a three-dimensional problem, you'd also get a del JP del Y, del JP del Z. In other words, you get the divergence of the current. But then let's look at a simple minus 1 over Q del JP del X as the first term for the time rate of change of the hole concentration at X as a function of time, okay? Now, in addition to currents flowing in and out, you can also have generation recombination of holes. So that is written as the generation rate per unit volume per second, G of P, minus the recombination rate. And the difference between the two, which I call UP, is the net recombination rate. And that whole constellation in this, say, n-type semiconductor P sub n minus the equilibrium value, Pn naught, divided by the generation recombination lifetime, which we introduced at the beginning of chapter 4. Okay. Now, Pn minus Pn naught is delta P. So that's a deviation from equilibrium. And that could be both a positive or a negative number. In other words, you could have an excess of carriers compared to equilibrium, in which case you have a net recombination rate, or this delta P could be a negative quantity. In other words, you might be depleting carrier constellation below the equilibrium value, in which case delta P would be a negative quantity. Okay. So anyway, the hypothesis is the recombination rate is proportional to equilibrium, either positive or negative. So that's the final term. Now, going back to the differential equation, the P itself can be written as Pn plus delta P. Now, Pn naught, of course, does not depend on time. So delta P delta T becomes delta d dt of delta P, which is shown over here, plus d dt of Pn naught, which is 0, right? Because Pn naught does not depend on time. So basically, I have converted this equation, differential equation, instead of as a function of P, I've converted that to a differential equation as a function of delta P, okay, as shown over here. You can get a similar expression for electron continuity equation. Next, what we did was we solved this differential equation for a particular problem. So you can think of the next page as a worked out example, but it's a very important worked out example which introduces the important concept of diffusion lengths, something that we'll be using in a second today, discussing PN junction diodes. Okay, so that problem that I'm solving is I have a semi-infinite bar in which at x equal to 0, I somehow create an excess whole constellation delta P. Okay. Now in this bar, I assume that there's no electric field. So then in the current expression, there will be no drift current. There will be no term equal to Q P mu times electric Q dP del x of P, which is the same as del x of delta P. Okay.
Professor, I
Yes.
just want to make sure you're not making any notations, are you?
No, I'm not in this case because
Okay.
yeah, I'm not on, but I'll start doing that in just a second. Okay. I'm actually, the presentation mode. I want to see how that turns out. Okay. Yeah. Uh,
Okay, because we can't see where your mouse is, so I don't think we can always see specifically what you're referring to on the
can you
page.
see the arrow?
Oh, I can see it now. What?
Okay. All right. So I wasn't showing that before. Okay. So capital delta P is the excess concentration at x equal to 0. Okay. And I'm solving the thing for no electric fields. Therefore, there's no drift current. Okay. So the question then becomes, if I write down the carrier continuity equation, I only have diffusion currents. And then furthermore, I'm solving this for steady state. So if I'm solving it for steady state, del T is just the diffusion current, which is minus Q dP del x of delta P. Okay. So since it's del x of JP, I end up getting the second derivative, del 2 del x square of delta P being the deviation of the carrier constellation from equilibrium, and then the q's cancel out. So from this middle term over here, you'll get dP second derivative d2 dx square of delta P, and then this term, of course, gives you delta P over tau P, and the whole thing is equal to 0 because I'm looking at a steady state problem. Okay, so that's what I have over here. Okay, so the second derivative of the deviation equals delta P. I divide throughout by dP, so that gives me dP times tau P. Okay, now that I write as a new term, LP squared, which is squared. Okay. Now, what is the solution of this differential equation? Well, you hopefully remember from your math classes that the second order differentiation, which is a constant C1 e to the power x over LP plus another term C2 e to the power minus x over LP. You have the two terms, okay? Then you apply the boundary conditions, and the boundary conditions are at x equal to 0, the excess carrier concentration is capital delta P, capital delta P over here, okay? So if x equals to 0, I get C1 plus C2, so that must be equal to capital delta P. And the second boundary condition is at x equal to infinity, the carrier concentration has to gradually go down to infinity. The second term vanishes, the first term blows up, meaning that C1 has to be equal to 0, right? So I get the solution as just C2 e to the power minus x over delta P. And furthermore, from the value at x equal to 0, I can identify C2 as being equal to delta P, okay? Now this quantity L sub P, as I mentioned, is a new term that I've introduced, and it's equal to the square root of dP times tau P. And if you look at the dimensions, that has centimeters square per second. Tau P has units of seconds. So dP times tau P, square root of that, has dimensions of length. And I see that the carrier concentration dies down exponentially with length, with a characteristic length constant, which is this diffusion length. And the physical meaning of that is it is the length, the distance, where the carrier concentration drops to 1 over E. Or in other words, you can also say that is the length, the average distance that the carriers diffuse before they recombine. Now, some diffuse more, some diffuse average distance they diffuse. Now, once I get this carrier concentration profile, which is this exponential profile, I can then go back and calculate the diffusion current. The formula for that is minus Q E sub P ddx of the carrier concentration profile. So I have to take the derivative of an exponential. And the nice thing with exponential functions is you'll remember that if you differentiate that, you get an exponential. If you integrate an exponential, you get an exponential. Okay, so if I differentiate this exponential function e to the power minus x over LP, I'll get 1 over LP, and I get the exponential back again. In other words, the diffusion current itself follows the same shape. It dies down exponentially, the distance. And that makes sense because if I look at diffusion current, that's proportional to the concentration gradient. The concentration gradients are going down. So that's why the diffusion current goes down. Okay. So this is a worked out example. But as I said, it's a very important example because it introduces this concept called the diffusion length. Furthermore, in a few minutes today, when you start looking at the IV characteristics of a PN junction, we'll see exactly this shape of a carrier concentration profile on the two sides of the junction. And we'll take the derivative and we'll get the corresponding diffusion currents from which we'll get the total current, okay? In a PN junction, we'll see that you have one region over here, say this is an N-type region, you'll have a P-type region on the other side, and in that, under forward bias, you'll inject holes, you'll inject electrons. Inside, you'll be injecting holes under forward bias, where this delta P or the delta N, which I'm not showing, are both a function of the forward bias of a PN junction. So keep that. So this slide is an important one, which summarizes all the key equations in semiconductor physics. And from now on, it'll just be an application of these sets of equations to different. We talked about the drift diffusion equations. So that's a drift term for the current density. That's a diffusion term. This is for holes. That's for electrons. Now, this also, of course, is true only for low electric fields. If I have a very high electric field, we saw that the mu p times E, which is the drift velocity, has to be replaced by the saturation drift velocity, either for the electrons or the holes. And then the total current would be the sum total of these two terms. So in general, in a semiconductor device, you can have electron drift plus electron diffusion, hole drift. Now, what we'll find, however, is in a practical device, not all four terms are going to be always important. In many cases, maybe only one of the four components is relevant at a particular location. Okay. Now, in addition to these equations, to solve device problems, we have to invoke the Maxwell's equations, which hopefully you remember from E325. But luckily, we only have to worry about one of the four Maxwell's equations, and that's the Poisson equation or Gauss's law, which tells you that the divergence of the electric field, dE dx, E is electric field, is given with the enclosed charge divided by the dielectric constant. So this epsilon is the dielectric constant. The Bohr would be Q, the charge of a hole, times all the positive charges, which is hole concentration plus exposed donors, minus all the negative charges, which would be mobile electrons and immobile acceptors. Okay, so P is equal to Q times P, the hole concentration, plus ND plus. The P is mobile, ND plus is fixed in the lattice, minus N, these are the mobile electrons which can move around, minus Na minus. Okay, so that's equal to dE dx, or the divergence of the electric field. Okay, now since electric field is equal to minus dx, you can also write that as the second derivative of the electrostatic potential with a minus sign. So we'll be solving this equation for different doping concentration profiles to get the electric field. You then introduce the electric field in the drift terms, and then when you apply a bias, you can have concentration gradients, and that'll give you the diffusion terms, and that's how all device problems will be solved. I sent you a video link for how devices are made called Silicon Run. So when you get a chance, you can start looking through it. So what I'm going to do next is so this is the analysis of the PN junction diode. But we'll get through it. Temperature, negative, exposed except black body radiation. You have to sell for 5 1 extensions beyond that one class extension because the solutions are going to be posted right after that. Okay? All right, with that, let's get started. So before spring break, you may recall we are talking about PN junctions in equilibrium. Can you hear the video? Slide over here, where you have 3 columns.
I can hear it, though it's a little bit muffled.
So the applied voltage is 0. That does not mean that nothing is happening, of course, because as I told you, the semiconductor is always in dynamic equilibrium with the environment. Absorb black body radiation, generate electron hole pairs, and after a few nanoseconds, they recombine and re-emit radiation. So that's what establishes Ni, which in silicon is 10 to the 10 per centimeter cubed at temperature. Anyway, so on the left-hand side, you can do a thought experiment where you take a p-type semiconductor doped with Na, and I'm showing that in the middle figure. So you have the majority carrier hole concentration equal to whatever the acceptor doping is, and then the corresponding concentration N on the p side would be Ni squared over Na, and similar things on the right-hand side. So then on the left-hand side, if you look at the band down below, you'll see that the formula was closer to the valence band. On the right-hand side, it's closer to the conduction band. And then when you join them, there'll be a spillover of the majority carrier electrons from the right to the left. And as the spillover, they leave behind the positively charged donor impurities which can't move. And that creates the depletion charge shown in this lightly shaded region on the right-hand side. And the electrons spill over, recombine with the holes which spill over to the right, and the holes leave behind exposed negatively charged acceptor ions. So the lightly shaded region forms what's called the depletion region with negative exposed acceptors on the left-hand side and positive exposed donors on the right-hand side. On the other hand, in the dark shaded regions, you have space charge neutrality, where there's no net charge, and that's because on the P side you have the positive mobile holes acceptors and the very few minority carrier electrons, n sub p. Okay, and similar expressions on the right hand side on n region. And as I told you, space charge neutrality is not universally true. It's only true if the doping concentrations are more or less constant. But in the vicinity of the PN junction, where the doping varies abruptly from p-type doping to n-type doping, space charge neutrality breaks down and you form these depletion charges shown by the shaded region. So then we discussed how you draw the band diagram. So as I told you, in equilibrium, you always have the Fermi level constant everywhere. So you first draw a horizontal line and you call that EF. And in equilibrium, EF on the P side equals that on the N side. So you have no variation of the Fermi level. Then you draw the rest of the band diagrams with respect to that. And what you do is you first draw it away from the junction because you know that the carrier concentrations will not be changed. So you have the conduction band closer to the Fermi level on the right hand side and the valence band closer to the Fermi level on the left hand side. Now the trick, of course, is figuring out how bands will vary with position within the depletion region. Okay? So that's what was discussed before the break, and I'll review that in a second. But also, you might position axis is position x, while the vertical position is electron energy, which has two components. It's only electron potential energy, but as you go up, you add kinetic energy to the electron. Okay? So these band edge variations are basically a variation of the electron potential, and that's shown in the middle row. And as you can see, the variation of the electrostatic potential is sort of the mirror image of the variation of the band edges, and that's because energy minus Q times P will go down. Okay. Now, exactly what is the shape of that curve in the depletion region? Now, what I proved before spring break is while it kind of looks like a straight line, sloping straight line, it's not really a straight line. It's actually a parabola with the curvature downwards and joining smoothly with the parabola with the curvature upwards. And that's what you have, of course, if you have so-called step junction. Now, step junction means you have uniform doping on the P side, doped at Na, and varying abruptly to another constant doping Nd on the N side. And that's the solution that we worked out before spring break. Of course, real PN junctions may not have such constant doping changing abruptly to another constant doping. But if I have this simple case, the math becomes simpler. Okay. Now, what we did first was solve for this built-in junction potential QV naught in equilibrium. And let me go back a couple of slides to refresh your memory about how we derived that before spring break. Okay? And what we did was, looking at the equilibrium case in more detail, we saw that you get equilibrium, which is a dynamic equilibrium. And let's refresh our memory as to how that happens. Well, after equilibrium is established and you build up this junction potential QV naught, you obviously have a potential barrier for over to the P side, right? Right, still does happen, but it happens at a reduced rate compared to the initial diffusion from the N to the P side, just at the onset of this whole process. Okay? Now, that reduced rate of electrons diffusing are only due to the electrons which have a kinetic energy greater than QV naught. Okay, but it still is going to happen. Okay. Similarly, you'll have holes diffusing from the left to the right, as shown over here, and those are shown by these two arrows for electron and hole diffusion. Okay. So, what is that balanced by? How do you achieve dynamic equilibrium? It is balanced by the fact that on the P side, although I have majority carrier holes, I do still have a few minority carrier electrons in the conduction band, given by Ni squared over Na. Now, these electrons in this part of the band diagram don't see any forces because there's no variation of the potential energy, but they are randomly moving around because of Brownian motion. So once in a blue moon, they'll accidentally appear at the edge of the depletion region, and if they do, now they see electric field and they're swept across. Okay, and that's this corresponding of electron drift and hole drift. Now you'll recall, of course, that the drift currents are given by the carrier conservation times the drift velocity, which in turn is given by the mobility times the electric field. And you'd think then that if this electric field in the depletion region change, this drift current will also change. But it turns out in this particular case, it does not change because it is a supply limited drift current. And what that means is you have so few minority carriers in the bands. It's only proportional to how often these minority carriers appear at the edge of the depletion region. And that does not change with the field or the bias. Okay, so that's important to keep in mind. Now, before spring break, we then came up with an expression for this built-in junction potential QV naught in two ways. The first is you set that sum of the drift current and diffusion current equal to zero because you have this dynamic equilibrium. And then, in simple algebra, you use the Einstein relationship, which is D over mu equals KT over Q. Electric field is equal to, and plugging those in and integrating from the P side to the N side, you're able to come up with an expression for the junction potential, which is the difference of the electrostatic potential Dn on the N side on the P side, and that gives you your V naught. And we're able to prove that V naught is equal to KT over Q, which is 26 millivolts at room temperature, times log of the majority carrier concentration on the P side over the minority carrier hole concentration on the N side. You could also write that in terms of the electron majority carrier concentration divided by the electron minority carrier concentration on the. So if I have the P sub P on the P side, that's given by Na. P sub N on the N side is given by Ni squared over Nd. So that's how you come up with this final expression over here. Okay, so that was the first way we calculated the built-in junction potential V naught. We solved the problem a second way by looking at the Poisson equation, which is shown over here. But the Poisson equation, which is one of the four Maxwell's equations, tells you that the divergence of the electric field is given by the net charge rho of x. It's a function of position x divided by the dielectric constant of the semiconductor. Now, in general, the charges have immobile donor positive charges minus immobile exposed immobile ionized plus mobile holes minus mobile electrons. Now, of course, all four of those terms may not be applicable in all scenarios. So, for example, in the depletion region, the mobile hole and the mobile electron concentrations don't apply. So I've not shown them over here. I only have the exposed donors and the acceptors. But even that depends on what part of the semiconductor I'm looking at. So I have only acceptor ions, which are negatively charged. On the N side, I have acceptor donor ions, which are positively charged. Now, in this particular example, you can see that I'm assuming that the donor concentration is higher than the acceptor ion concentration, and therefore the depletion rate on the N side, Xn naught, is slightly smaller than the depletion region Xp naught on the P side. Now, why is that? That's because the total exposed charges on the two sides, electron spills over and recombines the whole. It obviously exposes a donor on the N side and at the same time exposes a acceptor ion on the P side. Therefore, the total net donor charges must match the total net exposed acceptor charges on the P side. Now, once again, as I told you, in this particular example, I'm assuming I have a constant doping which changes abruptly to another constant doping. Practical PN junctions may not be that simple, but we make the simple assumption so that it can do the solutions analytically. Okay. Anyway, once you put those in, it's very straightforward. You have the first derivative of the electric field equal to this. Integrate that, electric field will be this quantity times x, because if you integrate a constant c, you get c times x. Therefore, this electric field varies linearly with. It also varies linearly with position with a different slope because the doping concentrations are different on the two sides. And then putting in the right boundary conditions, you find that the electric fields vanish at the edges of the depletion region, because beyond that, it has space charge neutrality. Okay. Now, once I get the electric field variations, I can solve for the potential variations, because we know that electric field E equals minus dV dx. So E is some constant times x. Therefore, if I integrate that with respect to x, V will be proportional to x squared, right? So therefore, if I integrate this, the potential variation will be proportional to x squared, which is the shape of a parabola. And if we integrate this side, it will also be proportional to x squared, but with a different sign, because the sign of the charges are different. And that's why I told you that if you look at the corresponding shapes of the electrostatic potential profile, you get a parabolic shape over here, joining smoothly with a parabola with an opposite curvature. And that's what's reflected in the band edges. Okay. Now let's go back to the solution of the Poisson equation for a second. So once I get this, you can integrate electric field between minus x p naught to x. And that, of course, in the simple case of linearly varying electric fields, is the area under the triangle. That's given by this expression over here. So that's another form of the v naught, which of course must be the same as the v naught that we derived a couple of minutes back, right? So that's what I show over here. So I plug in the value of way of calculating v naught over here, and that's how you can get an expression for the W entirely in terms of the doping concentrations Na and Nd, and that's a very useful expression over here. Now, not only can you get the total depletion rate, as I told you before spring break, you can also then figure out how much the depletion region spreads out on the P side versus the N side. And to do so, all that I need to do is remember that the total depletion charges on the two sides must match, right? And that's what's shown over here. So the total depletion charge Na times Xp must match Nd times Xn. And then, of course, you also have Xp plus Xn equals the total depletion charge. By solving those two algebraic equations simultaneously, you can come up with expressions for how much the depletion region spreads on the N side versus the P side. And what you'll find is the depletion region spreads out more on the lightly doped part of the junction and less into the more heavily doped part of the junction. Okay? And there's a worked out example that you can look at on your own. Now, looking at this particular schematic now, by looking at the form of the depletion regions, in this particular example, I'm showing that the depletion rate is the same on both sides. Be the same on both sides. But it doesn't have to be. It depends on what the conditions are. All right, now let's look at the second column, which is the case with forward bias, V equal to Pn. Okay. Now, if I apply a forward bias, which is the positive terminal of the battery connected to the P side and the negative terminal connected to the N side, what will happen is, because the band diagrams are electron energy minus Q times V, will go up, while on the P side, electron energies will go down. And basically what you do is you take the equilibrium band diagram and skew it as shown in the middle, meaning that the junction potential is now reduced to P naught minus Dn. Okay. Now what one finds is most of that applied forward bias will drop across the depletion region. There'll be a negligible amount of drop in the P at the N side itself. There will be a drop, but it will be much, much smaller. Now, why is that? Well, you can think of this PN junction structure as three resistors in series. Okay, you have relatively low resistance in the undepleted P side, in series with a very high resistance in the depletion region, and then a lower resistance in the N side. And therefore, if you apply a voltage VN, most of the voltage will drop in the middle part, which has the highest resistance. And that's why I'm showing that the band diagram varies as shown over here. It's V naught minus Vn is a new barrier potential. Okay. So once I have that, clearly it becomes more easy for these majority carrier electrons on the N side to diffuse across compared to the equilibrium case, right? Because now you have more carriers and lower energies which can go across. And that's what's shown by these arrows compared to the equilibrium scenario. Of the electrons and the holes increases. Now, at the same time, the electric field in the depletion region obviously goes down because of slow opposing drift current. But because this is a supply limited current of the minority carriers, these opposing drift currents don't change in magnitude. A very similar story is true for reverse bias. So now in reverse bias, the barrier increases. Diffusion current components basically go to zero, but the opposing drift currents don't change because once again it's a supply limited current. Any questions? If you have a question, you can unmute yourself and ask it. Or you can ask me later on during office hours. Okay? All right, now let's look at the PN junction in forward bias in a little bit more detail and come up with an expression for the forward current. Okay. So here, I'm now the PN junction structure in forward bias. And in this particular case, I'm assuming that the doping on the N side is slightly higher than the doping on the P side. How can I tell? That's because the depletion region on the N side is narrower than the depletion region on the P side. Okay. So N, NA. Okay. If that's the case, the minority carrier P on the N side, which is Ni squared over Nd, will be less than the minority carrier whole electron concentration on the P side, which is given by Ni squared over Na, right? And that's kind of what I'm showing over here. So because the majority carrier electron concentration is higher than the majority carrier hole concentration on the left-hand side, hole concentration is slightly lower than the minority carrier electron concentration on the P side, as shown by these dotted lines that I just marked off. And once I apply this forward bias VF, as I told you, the barrier potential changes from V naught to V naught minus Vn. Okay. What I now want to find out is what is the ratio of the majority carrier concentration, say the holes on the P side, over the minority carrier concentration of holes on the N side. Now that ratio we proved before spring break is given by e to the power q V naught over kT, right? If I go back a couple of slides, that's what we proved over here, right? So the ratio of the majority carrier concentration of the minority carrier concentration log of that gives you the V naught. That's what over here. And if you simply invert that, the ratio of the majority carrier concentration of the minority carrier concentration is e to the power q V naught over kT, right? So P sub P over P sub N, majority carrier over minority carrier, equals e to the power q V naught over kT. Okay? That's also true in terms of electrons, N sub N and N sub P. Okay? So that is what's shown over here again. Now it turns out that relationship is also true under bias. And all that will happen is you need to replace the V naught by V naught minus V forward, or in reverse bias, V naught plus V reverse. Okay. So that ratio is always going to be valid under bias also. But now you have a question. So now we have the majority carrier hole concentration on the P side over the minority carrier hole concentration on the N side equal to a lower number. Why is it a lower number? Because it's now E to the lower value, V naught minus Vn. So the ratio becomes exponentially lower. Then the question arises, is the ratio of the majority to minority carrier concentration lower because the numerator goes up, or the denominator, sorry, is the ratio lower because the numerator goes down, or the denominator goes up, or maybe some combination of the two? And the answer is, under so-called low level injection conditions, it is the denominator which goes up exponentially by that factor, meaning that P on the N side will be the starting value, Pn naught e to the power q Pn over kT. Let's prove that. Okay. The so-called low-level injection conditions. So let's explain what low-level means. The term low-level means that when I inject these minority carrier holes from the P to the N side as shown over here, you also get a corresponding increase of the majority carrier electrons on the N side in order to maintain space charge neutrality in this region. Space charge neutrality breaks down in the lightly shaded region, but in the dark shaded region, the space charge neutrality is maintained. So as a result, if I inject more positive holes, the only way you can retain space charge neutrality is if the majority carrier electrons also go up by exact amount. It will mirror that. Okay. Under low-level conditions, you assume, however, that the fractional change of the majority carrier N on the N side is negligible compared to the starting value. In other words, this delta N that I have to maintain space charge neutrality is much less than the starting value of electrons on the N side, Nd. And this is very similar to what I discussed in the problems at the start of chapter 4 in the case of optical generation of electron hole pairs, where you may recall we said that if you shoot photons at a semiconductor and you absorb photons and you create excess electrons and holes, although delta N is exactly equal to delta P, the fractional change of the minority carriers was humongous, but the fractional change of majority carriers was negligible. So it's that kind of a story over here. Okay, so the fractional change of the majority carrier electrons on the N side is similarly the fractional change of the majority carrier holes on the P side will be assumed to be negligible. Okay. So if that's the case, if this ratio over here, the only way the ratio can go down exponentially is if the denominator increases by that exponential factor as shown over here. And that's what I'm showing over here. So in this diagram showing the minority carrier constellation at the edge of the diffusion region will increase by this exponential factor Pn naught, where Pn naught is Ni squared over N times e to the power q Pn over kT. Okay. And that is the success. That's the first term over here. What I really want, however, is not the actual minority carrier constellation, but the excess minority carrier constellation. And all that I need to do is, from this, I need to subtract the starting value of Pn naught, which is given by Ni squared over Nd. So that should have been written as Pn naught. Okay. As a result, the excess is written by this term over here, while the start. If I add this term to this term, I get the total constellation Pn naught e to the power of q Pn over kT over here. Everybody with me? All right. Now, once I create an excess of minority carrier holes on the n side, compared to what the whole constellation is far away, I clearly establish a constellation gradient. And we've learned before spring break, anytime you have a constellation gradient, you give rise to a diffusion current. What is the form of the diffusion current? For holes, the diffusion current will be proportional to dP dx. The proportionality constant, the diffusion coefficient, with the minus sign. And to get the actual charge, you have to multiply by the charge of the hole, right? So it's minus q diffusion coefficient dP dx. dP dx, of course, is nothing but the slope of this curve. Okay? And therefore, by taking the gradient of this constellation profile, you can calculate the diffusion current anywhere. But before you do that, you obviously have to solve for this diffusion carrier constellation, this carrier constellation profile. Okay? And that, it turns out, is given by an exponentially decaying function, e to the power minus x over Lp. How do I get that? We'll get that equilibrium. Now, let me go back a few slides to what we discussed before spring break. At the end of chapter 4, we had worked out an example discussing this. So, before spring break, you may recall, we had looked at the continuity equation, which is this bookkeeping equation, which tells you that if you have current flowing in, JPX, and current flowing out at JPX plus delta x, and plus there's some recombination and generation going on, the time microscopic region between x and x plus dx is given by the difference of current flowing in minus current flowing out, which is nothing but the divergence of the current in 3D, or del J del x in 1D, plus the recombination and generation terms, which is given by this term over here, which is excess concentration over the generation recombination lifetime. That is your continuity equation. For holes, you have a similar expression for the electrons. Then all this for steady state. Now, if I have steady state, obviously this term would be equal to 0. And we had looked at the case where electric field was 0, meaning current would be equal to 0, meaning that the only current for holes would be this diffusion current minus q dP 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 dx. So that solution was this worked out example over here. So here what we said was we have a bar, we shine photons, we create an excess delta P. If you then solve the diffusion equation in steady state with only diffusion current, we got the second order differential equation, which has the solution in terms of growing and long, meaning the length is much greater than this diffusion length Lp, where Lp is the square root of the diffusion coefficient times lifetime. You can then ignore the growing exponential term over here, C1 equals 0, and you're only left with this decaying exponential term shown over here. Okay, so that was a worked out example of the continuity equation that we did just before spring break. Well, you can use the same kind of math over here. So you now have an excess of carriers in the PN junction, but by this forward bias. Okay? And if the PN junction region is very, very long, long meaning physically longer than the diffusion length, you only have this exponential term. The growing exponential term can be ignored. Okay? So that's what I'm showing over here. Everyone with me? If you have any pressing questions, you can always unmute yourself and ask the question. You know, one good thing is you'll have this recorded, so you can always go back and listen to my talk. Okay, so that's my delta P over here. excess over this PN naught begin with. Okay? And that's going down exponentially with distance, provided the length of this region is much, much longer than the diffusion length of the holes in the N side. All right. On the other hand, if it is a short PN junction that we'll discuss later on, you'll have both the decaying exponential term and the growing exponential term. Have these sage functions and cost functions and all that. And we'll discuss that in chapter 7 when I apply the same kind of math to the narrow phase region of bipolar junction transistor. Okay. The same kind of thing that I told you is also true, obviously, on the P side. Now, in this particular example, I've assumed that the P doping was lower than the N doping. The diffusion region is wider, and as a result, the starting minority carrier concentration of electrons is slightly higher than the carrier hole concentration on this side. But the rest of the math is very similar. You get an excess, which depends exponentially on the forward bias, -1. It dies down exponentially with distance. In this case, of course, as e to the power minus x over the diffusion length of electrons, ln. Okay. Now, once I get carrier concentration profiles, I'm home free because now, for example, for the whole current, diffusion current, I can simply write that as minus mu diffusion coefficient times the concentration gradient, right? dp dx. Okay. That's what I'm showing on the next slide. So here, once again, I'm showing the PN junction. Now, once again, I've assumed that the dopant concentrations are the same. If the difference is very straightforward, the diffusion region will extend and more in the lysodope side of the junction, and the corresponding minority carrier concentrations will have this inverse dependency, Ni square over Nd on this side, or Ni square over Na on this side. In the next figure over here, I'm showing just excess delta P and delta N as a function of position, while in the previous case, I'm showing the actual carrier concentration. So from this actual concentration, if we subtract the starting value shown with this dotted line, excess goes down to 0, right? While if I showed the total carrier concentration, the total carrier concentration would go down to whatever the background value is, PN naught or NP naught on this side. Okay. Okay. So now, as I said, to get the diffusion currents, very straightforward. It's simply given by the concentration gradient. Okay. Now, this concentration profile we just shown is proportional to e to the power minus x over LP times the starting value over here. What do I get if I differentiate that? But the nice thing with exponentials is you'll also get an exponential times 1 over LP. So if I take the derivative, d dx of this quantity over here, delta P, you get a function 1 over LP times the same function, e to the power minus x over LP. Okay. Well, if I was to plot the diffusion current as a function of position, that would have exactly the same shape. Okay. And the value of the current, of course, is going to depend on the diffusion length and all the prefactors and all that. But the shape is exactly the same as the carrier concentration profile. And that's why I'm showing that the diffusion current has exactly the same spatial as the excess carrier concentration profile delta N times this prefactor over here, which is QA diffusion coefficient dP divided by LP, and the denominator is I have to take the derivative d dx of this carrier concentration profile. Okay. Similar expression, of course, is true on the N side over here. All right. Now, you can clearly see then that the diffusion current is exponentially dying as a function. Now, that should bother you a little bit, because if I now try to solve for the current in a PN junction under DC bias, KCL, Kirchhoff's current law, should be valid, meaning that the current in any cross section must be the same. Okay. in steady state. The diffusion currents that I've calculated on the two sides of the minority carriers are dying down exponentially with distance. So something else must be picking up so that the total current is the same at any cross section. Okay. Now, before I get into the discussion, let me make a statement and then I'll prove that. Okay. And the statement is a very bold statement, and that is the total current I, which is same throughout, is sum total of the diffusion current of holes on the n side at x equal to 0, which is the diffusion edge over here, plus the diffusion current of electrons at this position on the p side. So let me restate that. I'm stating that the total current, which is same throughout the p in accordance with KCL, will turn out to be the sum total of the whole diffusion current at this location, which is given by this expression over here by plugging in x equal to 0, plus the electron diffusion current at this location, and that will be the total current anywhere in the structure. So that's the statement, and we need to prove that, of course. Okay? That's a very bold statement because, I mean, obviously ask, how can you say that by adding up diffusion current of holes at this location to the diffusion current of, how can you say that the diffusion current of holes at this location to the diffusion current of electrons at this location is the total current structure? Okay, I need to prove that obviously. But the guy who proved that is William Shockley, who I've mentioned several times already, the guy who won the Nobel Prize. And he made a bunch of assumptions which are known as the Shockley ideal diode approximation, which is not always valid, but we'll assume that it's valid for this derivation, and then we'll correct that in a couple of lectures later on. Okay. Now, according to Mr. Shockley, he said that in the depletion region shown in this lightly shaded region, you have no generation recombination of carriers. All the generation recombination happens outside of the depletion region. So when the minority carrier with the holes, which are majority carriers on the p side, diffuse across and now become minority carrier holes on the n side, they diffuse from the high concentration region to the low concentration region, recombine with electrons, and die down exponentially with distance. Similarly, the whole electrons from the n side diffuse across, now become minority carrier electrons on the p side, diffuse, recombine, and die down exponentially with distance. Okay? But all that recombination process happens outside of the depletion region. Within the depletion region, according to Mr. Shockley's ideal diode assumption, there is no generation recombination. That's an assumption. PN junction diodes. Okay? If you accept that, then let's look at the current components over here. So I've so far calculated the diffusion current holes, minority carrier holes on the n side at this location. Similarly, I've calculated the diffusion current of electrons at this edge of the depletion region over here. Okay. Now you'll notice one thing, that in this particular example, I'm not showing the depletion regions extending the same way on both sides. Okay. You should be able to tell that purely in this assumption, in this particular cartoon, I'm assuming that the depletion, that the doping concentration on the p side is higher than on the n. That's why this depletion region is narrower than this depletion region. And as a result, the minority carrier electron concentration n on the p side, which will be ni squared over na, is going to be less than the minority carrier hole concentration ni squared over nd on the n side. Okay. All right, so let's go back to the ideal diode approximation. So I first calculated the diffusion currents at the two edges of the depletion region. And then, if there's no generation within the depletion region, clearly this whole current must be the same as the whole current throughout the because there's no recombination that's going on. I'm showing the whole current component as being constant within the depletion region. All right. Same for the electron. Okay, the electron diffusion current that I've calculated must be the electron current throughout the depletion region. Okay. But how about the drift currents? Well, drift currents, I know, say for holes, are given by Q, cross-sectional area, hole low field region is the mobility times electric field, right? In this particular case, I don't have a supply limited current in these regions over here, okay? Similarly, for the electrons, you have this replaced by N, this will be BUN, right? So that will be for holes, and you have a similar expression for electron drift current, right? Let's see what those components of the drift current would be on the two sides. Because the drift currents are proportional to the carrier concentrations, on the P side, whatever the electric field is, clearly the majority drift current must be much, much higher than the minority carrier electron drift current, right? Because majority carrier concentration is much, much higher than the minority carrier concentration. So on the P side, the whole concentration is proportional to Na, while the electron concentration is much, much smaller. It's given by Ni square over Na. Therefore, the minority carrier electron drift current is going to be orders of magnitude smaller than the majority carrier current. Any questions? Okay, so there's a lot of moving pieces to the Shockley ideal diode approximation. I'm going to repeat that using first time. Okay. So what have I gotten so far? I've said that I've calculated the diffusion current of the holes on the N side on the previous slide, and because there's no generation recombination, I can say that's equal to the hole current throughout the depletion region, right? Similarly, I've calculated the electron diffusion current over here, and that's the same as electron current throughout, right? Now for the electron current, I've calculated the diffusion current, but there could also be a drift current, right? Proportional to whatever the electric is in this region. Now that's going to be a small electric field, but it will be non-zero, right? But even if there's a drift current, I've just proved that that drift current will be due to the whole drift current on the P side, right? Because the whole carrier concentration is much, much larger than the minority carrier electron concentration on this side. So as a result, for the total current, I, which is IP diffusion plus IP drift plus IN diffusion plus IN drift, those are the four current components in general. What I can say is, at this location over here, for instance, about the electron diffusion current, which I've calculated, I don't have to worry about the electron drift current, because if there was any drift current, that would be dominated by the majority carrier hole drift current. Okay? So as a result, you can write down the total current anywhere as the sum total of the minority carrier electron diffusion current at this location to the minority carrier hole diffusion current at this location to the minority carrier electron diffusion current at this location. And that is going to be a total current. Now the components of the current, however, will change with position. All right. Very, very far away from the junction, where the minority carrier concentration dies down exponentially and becomes a constant value, clearly there cannot be any diffusion currents anymore, right? So under those conditions, it will only have to be a drift current. What sort of drift current? It will be the majority carrier drift current. So on the N side, here, it'll be electron drift current. On the P side, it'll be hole drift current. While in the vicinity of the junction, it'll be a mostly diffusion current. So let's summarize what I said. Okay? PN junction, the total current has to be constant everywhere. That's shown by this constant I throughout. But the components of the current, IP drift, IP diffusion, plus IN drift, plus IN diffusion, those four components vary depending on where I'm looking at in the PN junction structure. Very, very far away from the junction, where there's no concentration gradients, it's only going to be drift current of the majority carriers. So what I have is, I have electron drift current of the majority carriers being fed towards the junction. As they go across this barrier in the depletion region, they become minority carrier electrons. So they now change to minority carrier diffusion current, which dies down exponentially with distance. And as it dies down, it's made up by the majority carrier hole drift current, so that the total current always is equal to the I throughout the structure. Any questions? Carefully, clearly, without having access to a whiteboard and a lot of space. So I think it was probably kind of confusing, but because it's so important, let me go over this again. Okay. So in the previous slide, I calculated the variation of the minority carrier concentrations with position. We saw that the excess carrier concentration depends exponentially. You subtract the PN naught. PN naught is constant throughout, of course. That's the minority carrier concentration background value. Because I've created an excess over here, it will diffuse from high concentration region to the low concentration region. That we then solve using the steady state carrier continuity equation, and that gives rise to an exponentially decaying function, e to the power minus x over LP, or e to the power minus x over Ln. Once I get the carrier concentration profiles, I get this exponentially decaying profiles. I can get the diffusion currents by simply taking the derivative of the carrier concentration profile, dp dx, times the corresponding diffusion coefficients. Because this carrier concentration profile was exponentially varying, if I take the derivative, that also is an exponential. Therefore, the shape of the carrier concentration current profile has exactly the shape as the carrier concentration profile shown over here. And that is shown in this figure. So the diffusion currents die down exponentially with distance on two sides. And then I made the bold statement due to Shockley, the so-called Shockley ideal diode approximation. It states that there's no generation recombination that assumes that goes on within the depletion region. If that is true, then the whole diffusion current that I've calculated on the N side must be the same as the whole current over here, right? There's recombination going on. Similarly, the electron diffusion current that I've calculated over here must be the same as the electron current over here. But you might say, wait a minute, how about the electron drift current over here? Well, on this side, the minority carrier electron drift current can be neglected compared to the majority carrier hole drift current. So of all these four components, I can always ignore the minority carrier drift current. Okay? So as a result, on the P side, I can say that as far as electrons are concerned, I only need to worry about the electron diffusion current. I can forget about an electron drift current. So this electron diffusion current that I've calculated is approximately the total electron current. And since there's no generation recombination within the depletion region, that is going to be the total electron current throughout. With the same argument, this is my total whole current throughout. Therefore, the total current I is going to be the sum of the electron current over here plus the whole current over here. And as a result, I can get the total I by adding up the whole current that I've just calculated over here to the electron current that I've calculated over there. Okay? And that is what's shown by adding up these two expressions over here. Any questions? Okay. A couple of other points about this band diagram. Once I apply this forward bias, obviously I'm no longer in equilibrium. The Fermi level is not going to be constant throughout. The Fermi level will split into quasi-Fermi levels. But the separation of the quasi-Fermi levels is a measure of how far from equilibrium I'm driving the system, and that'll be given by the forward bias Df. Okay. Now I can calculate this expression for the current by another technique which is known as the charge control model, and that is shown in this part of the figure. This is an alternative way of calculating the current, and of course the total value of the current should be the same regardless of how you do the calculation. Okay? So what does the charge control approach look like? That's shown in technique B over here. In the charge control approximation, what you do is you look at the total stored charge of holes QP or QN on the two sides of the excess minority carriers shown in the shaded regions QP and QN. Okay. The total stored charge would obviously be the area under this curve, right? Because you have to integrate delta P of x dx between 0 being the edge of the depletion region, to infinity. And that times the charge of the holes is what I'm calling Q sub P over here, okay? Times the cross-sectional area of the device, of course. All right? Now in the so-called charge control model, what you say is, I'm establishing a steady state excess charge distribution QP. Ejected holes are recombining with the lifetime of tau P. That's your generation recombination lifetime. Now, if they're recombining at a rate tau P, and I'm maintaining a steady state distribution, obviously I have to replenish holes at the same rate to make up for the loss. Otherwise, the charge distribution would not be a steady state distribution, right? Therefore, I can write down the current IP as the total stored charge QP divided by the lifetime, the generation recombination lifetime. Okay? So with forward bias, I've established this excess charge distributions. It's not changing with time, but these carriers are recombining at a rate of tau P. Maintain the same steady state distribution, I have to resupply carriers at the same rate. And that's the essence of the charge control model. It's a different way of calculating things, okay? So in the first approach, we calculated the current by taking the derivatives of these carrier concentration profiles to get the diffusion currents, while in the second approach, it's more of an integral that by the lifetime to get the current. And of course, the expressions for the current must match up regardless of how you do the calculation. Okay. And that's what's shown over here. In the first approach, I calculate the total current by adding up the currents that I've calculated in the derivatives. But in the second approach, I can add up the currents in terms of the lifetime as shown over here. Okay. Now they might look different, but it turns out they're exactly the same. Okay, and I want you to prove that to yourself by realizing equals square root of dp times tau p, or lp square means dp times tau p. Similarly, ln square equals dn times tau n. Okay, so look at these two expressions. The first calculated using technique A, and the second one calculated using technique B, and make the substitution of ln and lp using this, and you'll see that the two expressions. Okay, I want you to do that sort of as a homework problem that you did not turn in. Okay. See if there's anything else I want to say. All right, so by doing these calculations, you're finally able to obtain an expression for the IV relationship of a PN junction diode, which I'm sure you've seen in 438 or other classes. Where I generation is either this or the sum of this plus this times e to the power QV over KT. That's my diffusion current, exponentially with forward bias V, minus 1, that's an opposing drift current, which is the supply limited current, which is independent of the field or the bias. A plot of this is this IV as shown over here. So in forward bias, you have an exponentially increasing current. When V equals 0, e to the power 0 is 1, minus 1 gives you 0. When V is negative, this exponential term basically goes to 0, and I get minus I generation, where I generation is this expression over here. Okay? That's your expression of the I generation. And that's your e to the power QV over KT minus 1. Okay? So that was the PN junction in forward bias. In reverse bias, that should be easier to understand. So here, when I apply reverse bias, the magnitude of the barrier increases from P naught, which is the starting value in equilibrium, to P naught plus VR. The depletion regions will expand by solving the Poisson equation, because now you have to drop a larger voltage across it. The minority carrier concentrations, which are already low, basically get pulled down to 0, as shown over here. Okay. And the reason they get pulled down on the N side, as I've said, you have a few minority carrier poles, which over here don't see an electric fields. They're executing random Brownian motion. But then once in a blue moon, they appear at the edge of the depletion region. And if they do, on the N side, these minority carrier poles, once they appear at the edge of the depletion region, they see electric field, they swept right across. Okay. Similarly, on the P side, you have a few minority carrier electrons, which are executing random Brownian motion, don't see electric field, but currently appear at the edge of this depletion region. Boom, they see this electric field, and they swept right across. And as a result, the minority carrier concentration, which is already low, is pulled low at the edges of the depletion region. Because of this, you end up establishing a concentration gradient, and anytime I have a concentration gradient, you give rise to a diffusion current, right? So you have a diffusion current of holes. Similarly, you have a diffusion current of electrons. Over here. So that's your I generation current provided by the diffusion of these minority carriers that are getting swept across according to the supply limited current component. Okay, so that's the expression over here. So the first expression is calculating it using technique A by taking the derivative derivatives of the carrier constellation profiles. That's why you have the Ln and the Lp's in the denominator. And the second expression is in terms of the charge control model. We have the tau n and the tau p. We have the tau n and the tau p. And although these two look different, as I've told you, since Lp squared equals dp times tau p, you'll see that the two expressions are exactly the same. Okay. Now in reverse bias, the Fermi level also splits up into quasi-Fermi levels. But if you compare this with the splitting of the quasi-Fermi levels in forward bias, you'll see that the splitting happens in an opposite sense. Okay. In reverse bias, the quasi-Fermi level for holes moves farther away from the valence band than in equilibrium. Similarly, for the quasi-Fermi level for electrons, moves farther away from the conduction band, meaning that have fewer electrons and fewer holes in reverse bias than I have in equilibrium, which is exactly what you'd expect. While in forward bias, the splitting of the quasi-Fermi levels is such that the Fn moves closer to the conduction band edge, meaning I have more electrons than in equilibrium, because I'm forward biasing the structure and I'm flooding the structure with injected minority carriers. Similarly, Fp moves closer to the valence band. But the splitting, which is a measure of how far from equilibrium I'm driving the system, will depend on whatever the voltage that I'm applying. All right? Any questions? All right, so let's wrap up by looking at a worked out problem. So you have a PN junction with a certain cross-sectional area. In this case, I'm doping it more heavily on the N side, 100 times more than on the P side. So the depletion region on the N side will be 100 times smaller than the depletion region on the P side. The minority carrier hole constellation on the N side will be 100 times higher electron constellation on the P side. Okay. I'm going to calculate the current, but the diffusion coefficients. In the problem I've given you the mobilities. Well, that's not a problem because I can always convert mobilities to diffusion coefficients using the Einstein relationships. I've also given you the lifetimes, so I can calculate the diffusion lengths of the electrons and the holes, square root of d times tau. Okay. And then the current density prefactor ND. So that's your minority carrier hole constellation on the N side times dP times over LP. And then to get the current, I have to multiply by the charge of the carriers. That gives you current density. If I wanted current, you simply have to multiply by the cross-sectional area of the device, which in this case is 0.001 centimeter square. Okay. So that's your area over here. And then to get the current with a bias of 0.7 volts forward bias, it's your e to the power QV over KT minus 1. This is your prefactor over here. Okay. The prefactor is given by this. So if you look at this expression, which technique did I use to calculate the current? Now, clearly, I used technique A because I have the diffusion coefficients Ln and Lp in the denominator. If I use technique B, I have an expression in terms of the lifetimes, tau n and tau p, but you'd get exactly the same values ultimately because I'm calculating the current in two equivalent ways. Okay. So today's lecture is an important one, and I realize it was a difficult one. So I'd strongly advise you to listen to the talk again. There's a recording of the cloud because we'll need to use some of these concepts in this chapter on PN junctions. Okay. I'm sorry I couldn't explain it better. It's kind of hard to write on this iPad screen and not having access to the board really is bothering me. Stuck with it, I guess. Any questions? All right. See you on Wednesday. Good luck.
Actually, Dr. Banerjee, real quick, I had a question about one of the homework problems.
Okay.
So number 4.9, what it talks about is a uniform generation of EHPs in the bar. So my understanding of that is there's no gradient,
Right.
no diffusion current.
Right.
And so there's voltage applied across. So there's going to be some, for the small voltage case, minimal drift, and for the large voltage, very large amount of drift. The question is, what is the dependence of the mobilities on one another? It's asking us to find, or it gives us UP, or micro mu of P, and does not give us the mobility of the electrons. And as far as I can tell from my notes, the only ways to find one mobility is to either know its respective diffusion coefficient, or to know the respective velocity of drift.
Right. So if I didn't give you the mobility, there's a chart in chapter 3 which shows mobility as a function of doping. So you should use that chart to read out the other mobility. Okay.
Okay. So it just wants us to do a lookup. Like, it's not like we have to derive it.
No.
Okay.
Yeah.
And then for number 16, I did this one and I think I got it. All it really is just calculating the exponential, then taking the derivative and then plugging in numbers, right?
Right.
Okay. Sounds good. Thank you so much.